Okay. All right, let's get this. Yeah. Okay, so I'm going to look at this introduction to university mathematics. And, why am I looking at this? Because the rule is I can look at whatever I want as long as it's new and worthy, whatever that means. Anyway, so introduction to university mathematics. Skip the preamble, go to the synopsis. Oh, this is just really saying a bunch of topics that we're going to cover and putting a short list there. Okay, that's fine. Then there's the Greek alphabet. Now, I can recite the Greek alphabet, I believe. Alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, phi, chi, psi, omega, or phi, chi, psi, omega, something like that. But could I write it down from start to finish? Perhaps not. And so maybe I should get that skill. Okay. In due time. For now, though, I'm going to start with natural numbers and induction. So, we start by discussing the natural numbers, which we define in the following way. A natural number is a non-negative integer. That is, it is a member of the sequence 0, 1, 2, 3, and so on, obtained by starting from 0 and adding 1 successively. We write blackboard bold n equals 0, 1, 2, 3 in braces like that with a dot 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 or an ellipsis there for the set of all natural numbers. The curly bracket notation here indicates that the objects are grouped together as a set. A set is simply a collection of objects. We will discuss more about sets later. There is not universal agreement on whether or not to include 0 as a natural number. When discussing foundational material, it is more convenient to include 0, but you will sometimes see it not included, in which case the sequence starts at 1, as most of us more naturally start counting. This immediately highlights the importance of being clear about our definition. You will see a lot of definitions in the course of your degree. Sometimes they will seem a bit pedantic, but you will quickly find that it is helpful, indeed very necessary, to have clear and precise definitions of the objects and properties with which you are working. We are familiar with various properties of the natural numbers. For example, they can be added and multiplied. That is, if m and n are natural numbers, then we can construct m plus n and m times n, which are also natural numbers. The multiplication symbol, like that, the cross, is often omitted. Simply writing the numbers next to each other, mn, is understood to mean multiplication. A dot may also be used, especially when handwriting. For example, you might see things like 2.3 equals 6. Addition and multiplication are examples of binary operations. They take a pair of elements from the natural numbers and produce an element of the natural numbers. Two important natural numbers are 0 and 1, which are additive and multiplicative identities. meaning they have the properties n plus 0 equals n and n times 1 equals n for all n in the natural numbers. The symbol, that symbol right there, which is kind of like a mutated epsilon and kind of reminds me of the word, perhaps it makes you think of the letter E, in which case you can think that it means is an element of. And we read this as for all n in the natural numbers, or for all natural numbers n. In fact, another symbol, for all, which is like an upside down A, is often used in place of for all. But for the moment, I will keep writing that out in words. Another important property of the natural numbers is that they have an ordering. So we can write things like m is less than or equal to n. We can carefully define this less than or equal to symbol. And here's the definition. Let m and n be natural numbers. We write m is less than or equal to n to mean that there exists a natural number k such that m plus k is equal to n. Okay, so some comments about this. You wouldn't really say, wait, let me just restart my notepad as it's not picking up my pen. Like you wouldn't really say 2.3 like that equals 6. This is probably just a typographic error because of course this looks like 2.3, which is a decimal number. Instead, the dot goes in the middle of the line like this. And we call that dot interpunct. But usually you wouldn't actually see it with actual concrete numbers. Instead, you might see it with symbols like that. And the reason why is because it is too easy to confuse with the decimal point. Okay, and what else can we say? Okay, plus and times are binary operations. Because, as they say, they take a pair of elements from the natural numbers and produce an element of the natural numbers. But we could always just make another one, another binary operation. For example, I could do plus and then put a ring around it and then maybe put a line underneath. And then I do a colon and then an equal sign, and this is me defining that operation. This is me defining that binary operation. And here's what it does. Like that. So I haven't came up with a way to read this out loud yet. I don't know. I'll just call it op. 5 op 6 then would be, by definition, 5 plus 6 times 6, which is 41. Clearly, because multiplication gives you a natural number, and so does addition, this is going to give you a natural number as well. And it's not like addition and multiplication because it lacks this super basic property of commutativity. 5 op 6 is not the same as 6 op 5. Okay? And I like this. They've defined m is less than n in this way. M is less than n in this way. So we can take that further and be super pedantic and use all the logical symbols. So m is less than or equal to n is exactly equivalent to, logically equivalent to, this claim that there exists a number k such that m plus k is equal to n. And if you wanted to take it even further, you could even specify the domain of k, as in what set does k actually come from. But often this is left out because it's pretty obvious from the context that we're just talking about natural numbers, and that m, n, and k, and all the other variables we might come up with come from the natural numbers, unless we say otherwise. Okay. Now, as for m is greater than or equal to n, you could just define this like this, and then you don't have to come up with a new definition. It's building new definitions based on old ones that you already have. Okay, so so this less than or equal to symbol, this is an example of a relation, which we'll discuss more later. Notice that we have not actually defined addition and multiplication. I am appealing to our familiar understanding of what these operations mean. In fact, even our definition of the natural numbers is a little unsatisfactory if we want to build things up from nothing, since it implicitly relies on some notion of what the integers are, or of what it means to add 1. For the purpose of this course, we will rely on our basic intuition for these things, but it is possible to be more careful building on an axiomatic description of the natural numbers, that is, laying out some clear axioms, statements that we assume to be true as a starting point, and then deducing all other properties from those. More generally, this is something to be aware of for all of your courses. They will have different starting points. In analysis, you will start with the axioms for the real numbers and will be expected to carefully deduce other statements that you might intuitively think of as obvious. In more applied courses like introductory calculus, you may be expected to use your existing knowledge about how to differentiate functions despite having not yet defined carefully what a derivative actually is. It can be a bit confusing to start with, working out what you are quote-unquote allowed to assume in different contexts, but it is something you should gradually become more comfortable with. Mathematical induction. We now move on to talk about induction. The following principle is sometimes quoted as a theorem, although it follows directly from our definition of the natural numbers. In fact, it can be used as an axiom when defining the natural numbers in a more rigorous manner. Theorem 1.3, Principle of Induction. Let P of n be a family of statements indexed by the natural numbers. Suppose that P of 0 is true, and for any n, if P of n is true, then P of n plus 1 is also true. Then from these two suppositions, P of n is true for all natural numbers n. Induction is often visualized like toppling dominoes. The inductive step 2, corresponds to actually placing each domino sufficiently close that it will be hit when the previous one falls over. And the initial step 1, is often called the base case and corresponds to knocking over the first one. To use induction to prove a family of statements, we simply have to demonstrate supposition 1 and supposition 2. Here is a very straightforward example. For any n in the natural numbers, the sum from k equals 0 to n of k is n times n plus 1 all over 2. So in other words, this is making a claim that the sum of the first n natural numbers is n squared n all over 2. It's the familiar formula for the triangle numbers. Now, what about the proof? It is helpful to clarify what exactly the statement P of n is. In this case, P of n is simply the statement that given the equality holds for that particular n, clearly P of 0 holds, because for n equals 0, the sum on the left-hand side is 0, and the expression on the right-hand side is also 0. Now suppose P of n holds. Then the sum from k equals 0 to n plus 1 of k is, by definition, the sum from k equals 0 to n of k plus n plus 1, the natural number immediately after n. Now, we've supposed by the inductive hypothesis that this portion here can be replaced with n squared plus n all over 2. Then just multiply the top and the bottom of n plus 1 by 2 so that you can combine them into one single fraction. And you get exactly the statement P of n plus 1. So by induction, P of n is true for all n. The small square on the right here is used to signify that we've reached the end of the proof. Historically, the letters QED were used for this purpose, standing for the Latin quaderat demonstrandum, meaning what was needing to be shown, but that has largely gone out of fashion. In other symbols include a filled square, are sometimes used. It is also worth clarifying that LHS and RHS are commonly used abbreviations for left-hand side and right-hand side of an equality. When using them in your mathematical writing, make sure it is clear to which equality they relate. One other comment on the above proof is that we have noted at the side where we have made use of the inductive hypothesis. Such commentary on your algebraic manipulations can be extremely helpful in communicating your argument. Some of the proofs in these notes contain a bit more commentary than is necessary. For example, the first sentence in the proof above, because I'm trying to convey some of the thought process required to develop the proof as well as the proof itself. But a well-written proof should always explain any steps that are not just routine algebra. You will probably find you need to write many more actual sentences than you have been writing in maths at school. Okay, so let's see if we can do this from this proposition from start to finish. Okay, so first you say your proposition, and what actually is the proposition? That if you add up the natural numbers from 0 to n, then this is exactly equal to that. Now, I understand that you're supposed to understand what that means, and that, of course, but I'm a fan of really spelling things out like that. Now, proof. So what I would do is I would say base case. Like that. K equals 0. And that is just literally the number 0, which is, of course, equal to when I plug in 0, where n is, which is and I even do a little tick, because you can just see that that's true. Of course it's true when k is equal to 0. Okay. And then induction hypothesis. 1, 2, and then 3 will be the induction step. The induction step. So suppose for some wait, no, not suppose for some k. Suppose for some m. So what I'm doing now is I'm saying that I'm going to imagine that there's some m for which this actually holds. And now the induction step. We consider this is the thing that we're going to consider now, where we don't go from 0 to m, we go from 0 to m plus 1. Like, we're just saying, I wonder what this is, and I wonder what we can say about this. Well, we know by definition, like based on how sigma works and the sum of things works, this has to be where you go from k equals 0 up to m, and then you add on the very next case afterwards. And then this part here, well, in the induction hypothesis, we already presuppose that it's m times m plus 1 over 2. But you have to point that out. So I just say in brackets, by hypothesis, which is pointing to step 2. And then you just do what he calls routine algebra. Routine algebra. So it's like this. Which is like that. And that there is m squared add 3m add 2, which can be factorized into m add 1 times m add 2. And then you can, that's obviously exactly the same thing as the proposition for m plus 1. So if it's true for m, then it's true for m plus 1. And by induction, by the principle of induction, it's true for all n, for all the natural numbers, because we proved it for 0. We proved that if it's true for m, then that implies it's true for m plus 1, and therefore it's true for all of them. Okay. Now, now I go to the next bit. Family of statements holds for small n greater than or equal to big N, rather than necessarily small n being greater than or equal to 0. Okay, so it's saying corollary, which means a result that is an extension of or a consequence of a theorem or proposition. So what is this actually saying? This is saying that basically you don't have to start at 0. You can use the principle of induction, and you can just start from anywhere in the natural numbers. Like, let's say you have a set of propositions that you want to prove is true for every single natural number that's that's greater than or equal to the number 5. Then all you have to do, like, here's your proposition, your sentence about the number 5, and you want to show it's true. And for 6, and for 7, and for 8, etc. for all the natural numbers greater than or equal to 5. You don't care about 4, though. You either don't know or don't care about 4. Then you can extend the principle of mathematical induction such that this now is your base case. And then all you have to do is show that it's true for k, implies that it's true for k plus 1. Then it's true for any natural number that's greater than or equal to 5. Yeah. Okay. So yes, we use the word corollary to mean a result that is an extension of or a consequence of a theorem or proposition. A corollary is generally not such a major result as the theorem or proposition itself. The words theorem and proposition are used somewhat interchangeably to mean a result that one has proved, unlike a conjecture, which is something that has not yet been proven. Theorem is typically used for more significant results, and theorems are often given a specific name. We also use the word lemma to mean a result that is going to be useful in proving a later theorem or proposition. Lemmas are typically not such exciting or major results in themselves. Okay. Another variant on induction is when the inductive step relies on some earlier cases, but not necessarily the immediately previous case. This is sometimes called strong induction. Theorem 1.7, strong form of induction. Let P of n be a family of statements indexed by the natural numbers. Suppose that P of 0 is true. And suppose that for any natural number n, if P of 0, P of 1, P of 2, P of 3, all the way up to P of n are true, then P of n plus 1 is also true. Then it holds that P of n is true for all natural numbers. Okay. So what is this saying? This is, this is saying that this is really saying something like along these lines. First, you're going to suppose that P of 0 is true. And for P of n plus 1 to be true, for that to be true, all the prior propositions have to also be true. Like these collectively being true implies this. And if that's the case, if you have this and this holding and being true, then it's true for all the natural numbers. What's the proof? In fact, this is not really anything different, and we can straightforwardly convert it to an instance of normal induction by defining a related family of statements, Q of n. To do this, let Q of n be this precise statement that P of k holds for k equals 0, 1, 2, 3, 4, 5, all the way up to n. Then the conditions for the strong form are equivalent to Q of 0 holding and being true, and for any n, if Q of n is true, then Q of n plus 1 is also true. So to me, this feels a little bit like it feels a little bit like a bit of a cheat, like you're just rewording it, but I get it. It's like as if induction has been applied to itself. So you could get an even stronger form of induction, I think. Maybe you could. The following example illustrates how the strong form of induction can be useful. Okay, so we have this proposition. Every natural number greater than 1 may be expressed as a product of one or more prime numbers. What's the proof? Let P of n be the statement that n may be expressed as a product of prime numbers. Okay, that's logical. Clearly, P of 2 holds, since 2 is itself prime. That's true. Now, let n be greater than or equal to 2, be a natural number, and suppose that P of m holds for all m less than or equal less than n. If n is prime, then it is trivially the product of the single prime number n. And if n is not prime, then there must exist some r and s greater than 1 such that n is equal to rs. Now, by the inductive hypothesis, each of r and s can be written as a product of primes, and therefore n equals rs is also a product of primes. Thus, whether n is prime or not, we have that P of n holds. By strong induction, P of n is true for all natural numbers. That is, every natural number greater than 1 may be expressed as a product of one or more primes. Okay. Related to induction is the idea of recursion as a method of definition. For example, supposing we are happy with what it means to add 1, we can recursively define more general addition on the natural numbers. Define addition on the natural numbers by the rules that for all m in the natural numbers, m plus 0 is just m. Okay, that's logical because it's the identity. And 2, for any n that you have this definition right here. M plus brackets n plus 1 is equal to brackets n plus n all plus 1. Okay, so that's kind of cool. We can prove these properties instead of just like assuming them. All right, so that's kind of a challenge, isn't it? Can you actually prove that it's associative, that addition is associative given that definition of addition? So how does addition work? We're told this, and then I guess we're told this. Okay, so prove associativity of on. Okay, how are you going to do that? So first, here's what it says. Okay, so base case. Z is equal to 0. Like, is this true? Well, that's a natural number, and I'm adding 0 to it. So it's just the natural number itself, isn't it? And now, if I think about the number y, the natural number y, I can just do the definition backwards. So there you go. Assume it's so for like z is equal to k. Wait, do I have to use strong induction for this? I don't know. Okay. Then okay, now consider that, right? That's what we do, isn't it? Okay. No, wait. Oh yeah, this is actually wrong here. This should be I. Okay, so then I would say this. Not too sure what to do now. Like, what is even our goal? Our goal is to get here, isn't it? Oh yeah, okay, so I have no... Yeah, I have no basis for doing that. Yeah, I messed up. Okay, he starts at the same place that I do for 0. That's totally fine. Okay, so he says, in this fancy way of saying it, we induct on Z. So first, suppose Z is equal to 0. All right, that's what I did. Then for X and Y in the natural numbers, that's essentially what we did, but I guess, yeah, just backwards, that's all. And that's totally fine. Where we have used rule 1 from our definition of addition. Now, for the inductive step, suppose that the proposition is true for Z equal to N, and consider the case where Z is equal to N plus 1. Right. So he starts there. What enables him to move the brackets in this way? To go from there to there. Let's think what enables him to go from there to there. Part 2. Part 2 of the definition of addition. Then what's going to be intermediary step now? Moving that big bracket just there like that. And I'm aware that that's above there. But just for now, I just want to think, like, what actually warranted him doing that? Okay. Part 2 of the definition, right? Okay, so I have it now. So I started out there, and then by part 2 of the addition definition, I turned it into that. Then by the hypothesis, it's that. Then I can go to here by doing 2 again, and then again. Right, so that seems okay. Yes, look, see? Part 2, inductive hypothesis, part 2. And because mine is backwards, part 2, hypothesis, part 2. Okay, so that's cool. Thus, addition is associative. We can use a similar approach to define multiplication and factorial. For example, define multiplication on the natural numbers by the rules that for all m in the natural numbers, m times 0 is equal to 0. Okay. And part 2, for any natural number n, m times n add 1 is m times n plus m. Okay. And define the factorial on the natural numbers by the rules that 0 factorial is 1 and n add 1 factorial is n factorial times n add 1. That makes sense. Here is another property of the natural numbers that we can prove using induction. The well-ordering property of the natural numbers. Every non-empty subset of the natural numbers has a least element. We have not defined a subset, but maybe you can guess what it means. S is a subset of the natural numbers if every element of S is also an element of N. Non-empty means it contains one or more elements. Okay, so it looks like they're going to prove this by contradiction. So what does that mean? Proving by contradiction. It means, imagine the complete opposite of what you're trying to prove, the logical opposite, and then show that that leads to absurdity. And therefore, the original proposition itself must hold. Some people reject that this is an okay way to prove things. And I think they're called like constructivist mathematicians, and they say that that's not a proper proof. All you've done is shown that basically, in most people's minds, a proposition is true or it's not true. And you have to choose one or the other. And they can't both be true, and it can't be the case that neither is true. And so what people do is they show that this is totally bonkers and absurd, and then we have no choice. We have to accept this. And constructivist mathematicians say, no, that's not valid. All you've done is you've just shown this is not true. That's all. And they reject that you go over there. That's what I've heard them say. Okay. So they're going to prove this claim, the well-ordering property of the natural numbers, by contradiction. Suppose for a contradiction that there is a non-empty subset S that does not have a least element. A least element is sometimes called a minimal element or a least member. Various phrasings mean the same thing. We define S star to be the set of natural numbers that are not in S. In other words, the complement of S. And we aim to show by induction that in fact S star is the set of natural numbers itself. Since that means S is empty, which provides the contradiction. Okay, so what does the well-ordering property say? Here's the natural numbers, and it says, if you find me a subset, call it S, then there is a super special natural number in there, which is the least one. As long as S is not empty. As long as S is not empty. And what they're going to do is they're going to say, okay, let's pretend that it's not true. Let's pretend that the well-ordering property is not true. Then what I'm going to do is I'm going to consider everything that's not in S. Okay? And then by just investigating S star, I'm going to prove that this guy has to be empty, which is a contradiction. It contradicts your supposition that such a subset of N exists, a subset which doesn't have a minimal element. Okay, so how does it go? It says, let P of N be the statement that S star contains N. For the initial step, note that 0 is not in S. Of course it's not in S, since if it were true, then S would have a least element, namely 0. So, of course, 0 cannot be in S. It can't be in S. And therefore, 0 has to belong where? In here. 0 has to be in there. Therefore, P of 0 holds. Now suppose that we did the same thing, and it holds all the way up to P of n. Then n plus 1 cannot be in S, because if it were, then it would be the least element of S, since by the inductive hypothesis, all the smaller elements of the natural numbers are not in S. And hence, n plus 1 is here. So like 0, 1, 2, all of these guys are in there. And that implies that n plus 1 must also be in S star. And so by strong induction, which is here, 1.7, n is in S star for all natural numbers n. And therefore, this has to be empty, which contradicts our initial assumption that it's not, which proves the result. All the natural numbers have to be well ordered because of this. Okay, so here we have laid out the proof by carefully defining the statements P of n involved in the inductive argument. We can often get away without doing this quite so explicitly, and that is acceptable so long as the logic is clear. Indeed, it is not a good idea to make a proof unnecessarily long-winded. But when developing a feel for how such proofs work, and especially if you start to find yourself confused about your argument, you may find it helpful to be explicit like this. The well-ordering property of the natural numbers is one that you may well think is obvious, though note that the same property is not true of the real numbers, for example, so it is not an entirely trivial property. Here we have used the principle of induction to prove it. In fact, the well-ordering property is essentially equivalent to the principle of induction. It is also possible to work the other way and use it to prove the principle of induction. Okay, so now we actually get a theorem that's actually based on the well-ordering property, which proves that it's useful to some extent. Okay, so we have a set of natural numbers such that P of n is false. Oh, theorem 1.3, I get it. Oh, right. Okay, so they're going to prove the principle of induction using... Okay. They're going to prove the principle of induction using the well-ordering property. I see. And again, they use proof by contradiction. And binary logic. All statements are true or false. Okay. So next I'm going to look at the binomial theorem. It's a very, very famous theorem, isn't it? Something which you can like take for granted, memorize, and apply without knowing why it's true. We next aim to prove the binomial theorem, which provides the rule for how to expand a product of the form x at y to the n. Yes, this is very well known, that for the natural numbers n and k, we define the binomial coefficient like this. So what does it mean? This can be written like this, and you read it out loud as 5 choose 2. And it's, if you hold up your hand, it's the number of ways you can put up 2 digits. Like, there's a number of ways. And the answer to this is 10. There's 10 ways to do that. And some obvious things about it are, for example, like this, these are going to be the same. And n choose k is the same as this. And think of it like light switches. The number of ways to choose 2 things from 5 is the same as the number of ways to not choose 2 things from 5, which is the same as choosing 3 things. Like, how many ways can you stick up 2 digits is the same as how many ways can you put down 3 digits. It's the same question, but upside down, upside down. Okay. Pascal's triangle. It's very famous, in which the nth row contains each of the non-zero n choose k. Okay, so the following result is an algebraic expression of the defining feature of Pascal's triangle, that each entry is the sum of the 2 entries most immediately above it. This is Pascal's identity. So it's just saying that this 10 comes from this 4 plus this 6 added together. N choose k minus 1 plus n choose k is n plus 1 choose k. So how do you prove it? How do you prove it? Because, like, you can use this rule to make the triangle, but that does not prove that this triangle, the entries in this Pascal's triangle, are the same as the coefficients in the expansion of x plus y to the n. Like, how do you know? Maybe it's only true up to 100. Why not? You haven't investigated the entire triangle. So you have to prove it's true by induction. You have to prove it's true. And all you do is you just put in these entries here into the definitions and just do routine algebra like this. Okay, so how did he go from here over to here? What did he do? Right, so what is Pascal's identity saying? First, if I do this is way too abstract. Nobody understands what you're saying. So make the triangle. 0, 0, 1, 0. Sorry, 0, choose 0, 1, choose 0, 1, choose 1. 2, choose 0, 2, choose 1, 2, choose 2. 3, choose 0, 3, choose 1, 3, choose 2. 3, choose 3. Okay, and so what it's saying is that this entry here is this entry plus this entry. So the top number, you add 1 to it, and yeah, so okay, so what, like, do another one that's like really far down. Okay, 17, and let's say like 10 and 11, then logically this would be the same thing as 18, choose 11, like that. And that's the pattern. That's the pattern. Okay, so now you have to prove it. Prove it, prove it. Okay, definition of the choice function. How does it go again? Okay, we'll do it in red. N factorial over n minus k factorial times k factorial. Just put things in just like this. Okay, so over here it should be n take away this, which is n take k plus 1 factorial, and then it should be this factorial. There. This one is straightforward. And now you have to combine them. Now you have to combine them somehow. But how did he do it? How did he do it? Okay, so like he would have used the definitions, the definition of what factorial means. So is k minus 1 factorial equal to k factorial? No, you have to multiply it by k, and then it's equal. Then it's equal. So he would have multiplied this bit by k to get it equal to this bit. But then you have to multiply the top by k as well. Okay, so we're going to times the top and the bottom by k over there. But then what's the relationship between this bit here and this bit? So, okay, So I don't think in algebra, I think in numbers. So I'm going to ask myself, what is the relationship between this? I'm just going to use 17 and 7 for n and k. And this. What's the relationship? Well, this one over here, you have to multiply it by this, don't you? Because that's 10 factorial. That's 11 factorial. And so you have to times this by 11. And where did you get 11 from? I got it from 17 minus 7 plus 1. And what does that mean? That means n minus k plus 1. So over here on the right, I have to times this by n minus k plus 1 on the top and bottom, on the top and bottom. Wait. Hold on. And this here has to be multiplied by k. Okay, so now you can combine them together because you found the least, the lowest common denominator. So what was it? So it's going to be this on this times this. That's going to be on the bottom. And then this is what's going to be on the top. Or so I believe. Okay, now it looks exactly like that, doesn't it? I just have to factor out n factorial, and that is going to be added to that, which means that k and the minus k will cancel out. So I'll have n plus 1. And these will be multiplied together. And so it's looking really close now to this, isn't it? Because what is the definition of this? What is the definition of n add 1 choose k? Well, if I look up here, I just need an n plus 1 in that spot up there, and an n plus 1 minus k there, and then I'm good. So I have that. The denominator is perfect. But now I have to think, what is n factorial times n plus 1? Well, by definition, that's just exactly the same as n plus 1 factorial, isn't it? And so now we have exactly what we want. Okay, so perfect. All right. So let's see. This lemma can be used to show by induction that the binomial coefficients are integers rather than just rational numbers. A fact that is perhaps not immediately obvious from the definition. Okay, so what is he saying there? He's saying that, look, I've defined n choose k like this. It's a fraction. What is your basis for believing that this is a whole number? N factorial over k factorial times n minus k factorial. How do you know that it's a whole number? How do you know? It could be whole numbers up to here, up to the 100th row, but then it could just start introducing fractions for no rational numbers like 2 over 3 for no reason. So here you can show that that cannot possibly be the case. You have 2 integer entries here and here, and then you generate an integer entry here because when you add a pair of integers, you get another integer back. Okay, so now we are now in a position to prove the binomial theorem for non-negative integer exponents. Okay. Right, okay, I'm going to bookmark it there and go and read something. Be well.